So the idea of amplitude modulation is to apply the multiplication property to the scenario where you have a message signal x of t and a signal that we usually call c of t, which stands for carrier. So it's like the carrier signal. And what the multiplication property tells us is that in the frequency domain, it's going to give you 1 over 2 pi x of j omega convolved with c of j omega. Now, in the usual amplitude modulation setting, that carrier is a sinusoidal signal, like a cosine of omega naught t. And so what's the transform of the cosine? Well, we saw over here, it looks like these two impulses. So the way we write that is pi of delta of omega plus omega naught plus pi times delta of omega minus omega naught, so written like that. And now what we do is we let x of t be a bandwidth limited signal. So it could be music, could be in some kind of an audio signal, any signal you want, but in applications it's often that. And what we do is we multiply that message signal x of t by the carrier, by c of t. And what the multiplication property tells us is that the transform of that modulated signal, which is x of t, c of t, or x of t cosine omega naught t, is going to become 1 over 2 pi times the convolution of x of j omega with the goalposts, with the convolution of, with the transform of the cosine. Again, what's the easiest thing to convolve with? An impulse. You just take the thing that you're convolving with the impulse and you just move it to the location of the impulse. So if that impulse is located at minus omega naught and this one is located at plus omega naught, we're basically going to take a copy of x of j omega and just move it to the left by minus omega naught and move it to the right by omega naught. So we apply the shift in the frequency domain by minus omega naught and plus omega naught, and we add them up. So we end up with, we have to multiply by 1 over 2 pi. This had a pi in front of those goalposts, so that becomes 1/2. So basically what it says is we take a copy of x of j omega, we shift it to the left by omega naught and scale it by 1/2 in amplitude, and we take a copy of x of j omega, shift it to the right by omega naught and scale it by 1/2, and then we add them up. We add those two things up. So what does that look like pictorially? It looks like this. This is the formula. A copy of x shifted to the left and to the right, scaled by 1/2 and added up. Here's our x of j omega. Let's say it's bandwidth limited where the maximum frequency is omega sub m. And we have as our carrier signal a cosine, which you can read that as omega naught. This is omega sub c. Sometimes people use that for the carrier frequency. We're convolving this with this. And what does that signal look like? What does that convolution look like? It looks like this. And so this is what we get conceptually. Now, why do I say conceptually? Because here I've assumed that my omega sub c, the carrier frequency, the frequency of that sinusoid, is bigger than the maximum frequency of the signal. And because of that fact, that means that the left-hand edge, when we shift to the right, the left-hand edge of that transform, of the spectrum of the signal, is going to be above 0. It's the left-hand edge is at omega sub c minus omega sub m. When we take that thing and shift it to the left by omega sub c, again, this right-hand edge is going to go past the omega equals 0, and it's going to be at minus omega c plus omega m, which is over here. So the two copies don't hit each other. If I had chosen my carrier frequency to be less than omega sub m, these guys would overlap. So you'd get some weird kind of contributions in the middle that come from here and from here. But when it's bigger, when omega sub c is bigger than omega sub m, you get these nice, clean, separated copies. So it looks like, well, there's the spectrum of the signal just sitting out there, completely, perfectly unadulterated. It just happens to be shifted in frequency. And when that happens, that allows you to then recover the original. So the way in which we now, why do we do this modulation? Well, when we want to transmit through the atmosphere, it turns out that if you are actually trying to transmit signals that are in the 20 kilohertz range, they're not going to go very far. But if you use them to modulate a carrier, which is at a high frequency, like think of your AM radio type frequencies, then that resulting signal, which has a spectrum like this, but which is centered at one of those AM radio signal frequencies, that's going to transmit a long way through the air. And so that's the reason you modulate it. Now that's all great. That means that your signal gets to the destination across the country or something. But how do you get the original audio back? I mean, this thing is not, if you try to put this through your speaker, if it's up there in the hundreds of kilohertz or more region, you're not going to hear it. So what you have to do is you have to demodulate. You have to take the thing that was transmitted, the modulated signal, the modulated carrier, and you have to somehow bring it back to the original. And the beauty of this scheme is that the way you bring it back is you do exactly what you did to create the modulated signal. Y of t was this guy. This is y of j omega. So it's the signal that has this transform. You just multiply it by the same carrier signal, multiplied by the same cosine you used to get this in the first place. What does that tell you to do? Well, it tells you that the new signal that you created by doing this demodulation step is going to have a transform which looks like this, but shifted to the left by omega naught, and shifted to the right by omega naught, and then added up and scaled by a half. When you actually plug in for y of j omega, when you plug this in for y of j omega, just imagine visually taking this guy, shifting it to the left by omega naught. So this guy is going to actually get right back to the middle. This guy is going to go over to negative 2 omega sub c. Shift it to the right by omega sub c, or omega naught. This is going to go over here to be centered at 2 omega sub c. And this piece is going to end up centered at 0. So when you do that convolution, which is shown here graphically, you end up with, you really have 4 copies of this that are created, but 2 of them land right on top of each other. And when you think about what the scale factors of a half do, you end up with a copy of x of j omega shifted over by minus 2 times the carrier frequency, scaled by a quarter. You have a copy over at 2 times the carrier frequency, scaled by a quarter. And then the 2 copies that were shifted to the middle to be centered at 0, each had a scale factor of a quarter, so when you add them up, you get a half. And look what you have. You have a copy of x of j omega right where you want it to be, not shifted anywhere. It is scaled by a half, but we know how to undo a scale factor of a half. Just multiply the signal by 2. So now all we have to do is to figure out how to get rid of these guys, because we don't want them. What we're after is this. And the way we do that is by just applying a low-pass filter. So we just apply a low-pass filter to that demodulated signal, and we're going to pluck out that copy of x of j omega. So this was the signal that we got on the receiving end by multiplying by the cosine. Here's the spectrum. Now we just multiply by a low-pass reconstruction filter that filters out this guy and this guy, leaves us with this, and then we put in a gain factor of 2, and lo and behold, what we get is just our x of j omega back. So this is schematically what we did. We took that modulated signal, the transmitted signal that we then receive at some distant location. We multiply by the cosine. Here there's no phase factor we have to worry about. And then we just run it through a low-pass filter, and out pops our x of t. Okay? So that's the idea of the amplitude modulation.